Okay, stop what you're doing. Put down your phone. Or keep holding your phone because you're watching this on your phone, but mentally put it down. I need you to really be here for the next few minutes because what I am about to tell you is the most important thing. I'm going to explain everything. The entire universe, all of it, every atom, every galaxy, every thought, every star that ever burned, and every black hole that ever swallowed one. The beginning of time, the possible end of time. Life, consciousness, reality itself. Let's start at the very beginning, and I mean the very beginning. Not the beginning of human civilization beginning. Not the beginning of Earth beginning, the beginning. The moment everything, space, time, matter, energy, the laws of physics themselves came into existence, we call it the Big Bang. But here's your first mind bender of this video. The Big Bang was not an explosion in space. Let that sit. Most people imagine it like a bomb going off in a dark, empty void, a fireball shooting outward into nothingness. That is wrong, and it's wrong in a fascinating way. The Big Bang was not an explosion in space. It was an explosion of space. Space itself did not exist before it. Time itself did not exist before it. There was no before. There was no outside. There was no void waiting to be filled. Approximately 13.8 billion years ago, everything that exists, the entire observable universe, all the matter, all the energy, all the space, was compressed into something unimaginably small and unimaginably hot. Smaller than a proton, smaller than anything you can meaningfully visualize. And then it expanded, rapidly, in every direction simultaneously. Not into anything, not from anywhere. It just began. Within the first second, the universe was unimaginably hot, over a quadrillion degrees. Within 3 minutes, the first atomic nuclei were forming: hydrogen, helium, a tiny bit of lithium, that's it. The entire universe was just these 3 elements, spreading outward, cooling down, beginning the long, slow process of becoming. And here's something that should haunt you a little. We still don't fully know what caused the Big Bang. We know what happened after it with extraordinary precision. But the moment itself, the very first instant, remains one of the greatest unsolved mysteries in all of science. Some physicists suggest our universe was born from another universe. Some suggest it emerged from quantum fluctuations in an eternal field of energy. Some say the question itself might not be meaningful because cause and effect requires time, and time began at the Big Bang. There is no before. The universe is embarrassingly big now that we have a universe. Let's talk about what's in it. After the Big Bang, over hundreds of millions of years, gravity pulled that hydrogen and helium gas together into clumps. Those clumps got denser and hotter until something incredible happened. Nuclear fusion ignited. Atoms began smashing into each other with enough force to fuse together and release staggering amounts of energy. Stars were born. And stars, I need you to appreciate this, stars are the most important objects in the universe for us because everything you are made of, except hydrogen, was forged inside a star. The carbon in your body, the oxygen in your lungs, the iron in your blood, all of it was created in the nuclear furnaces of stars that lived and died long before our sun was born. Carl Sagan said it beautifully, we are star stuff. And that's not poetry, that's chemistry. Now let's talk about scale because the human brain is genuinely terrible at understanding cosmic scale and I want to break yours a little bit. Our sun is about 1.4 million kilometers in diameter. That's roughly 109 Earths lined up side by side. Already impressive, right? But our sun is an average-sized star. There are stars out there, Scuti, for example, that are so large that if you placed them where our sun is, they would extend past Jupiter, the giant planet that could swallow 1,300 Earths, and our sun is just one star. In our galaxy, the Milky Way, there are somewhere between 200 and 400 billion stars. We don't know exactly. We've never counted them. We can't. It would take longer than the age of the universe to count to 400 billion, even counting one per second. And the Milky Way is just one galaxy. The observable universe, the part we can physically see from Earth, contains roughly 2 trillion galaxies, 2 trillion, each with hundreds of billions of stars. Each star potentially hosting planets. The number of planets in the observable universe is estimated to be more than the number of grains of sand on every beach on Earth by a lot. And the observable universe is not the whole universe. It's just the part from which light has had time to reach us in 13.8 billion years. The actual universe may be infinite. We genuinely don't know. Take a breath, we're just getting started. You are mostly nothing. Let's zoom back in. All the way down to you, your body, your hand. The screen you're holding, everything you consider solid in your world is, at the atomic level, almost entirely empty space. An atom, the building block of everything, is made of a nucleus surrounded by electrons. The nucleus is incredibly tiny compared to the atom as a whole. If an atom were the size of a football stadium, the nucleus would be the size of a pea at the center. Everything else, all that space in between, is effectively empty. You are more than 99.9% empty space. The reason things feel solid is not because matter is packed tightly together. It's because of electromagnetic forces. The electrons in your atoms repel the electrons in other atoms, creating the sensation of resistance, of solidity, of a table, of a floor, of your own face. You have never actually touched anything. The electrons in your fingertips have never made contact with the electrons in your phone. They've only repelled each other close enough that your brain interprets it as touching. Sit with that. Now let's go deeper. Inside the nucleus are protons and neutrons. Inside those are quarks. Quarks come in types: up, down, charm, strange, top, bottom. Yes, those are real scientific names. Quarks are bound together by particles called gluons, exchanging the strong nuclear force. And here's where it gets philosophically dizzying. When you try to observe a quantum particle, a quark, an electron, a photon, you change it. Particles don't have definite positions until they are measured. They exist in superpositions, multiple states simultaneously, until observation collapses them into one reality. This is not science fiction. This is quantum mechanics, the most precisely tested theory in the history of science. And it means that, at the most fundamental level, reality itself is probabilistic, not determined, not fixed, fuzzy. The universe, at its core, does not know where anything is until something looks. Which raises a question we're going to come back to. What counts as looking? Part 4. Space, time, and relativity to 12 o'clock to 15:30 time is not what you think. Here's another thing your brain is bad at. Understanding that space and time are not separate things. They are a single fabric. Physicists call it spacetime. Einstein figured this out in 1905 with special relativity and in 1915 with general relativity. And what he discovered broke physics and then rebuilt it better. Here's the core insight. The faster you move through space, the slower you move through time. If you got on a spaceship and traveled at 99% the speed of light for what felt like 1 year to you, when you came back, Earth would have aged by about 7 years. You would be 6 years younger than your twin who stayed home. This is not theoretical. This is not a thought experiment. This is a real, measurable, verified phenomenon. GPS satellites have to account for relativistic time dilation every single day, or your maps would be off by kilometers. Time runs slightly faster at higher altitudes. We have measured this difference between clocks on mountain tops and clocks at sea level. Time literally ticks at different rates in different places, and mass, gravity, curves spacetime. The Earth curves spacetime around it, and what we call gravity is actually objects following the curved path that spacetime creates. The Sun curves spacetime more dramatically, and all the planets follow those curves. A black hole curves spacetime so severely that not even light, the fastest thing in the universe, can escape. A black hole, let's talk about that. When a star massive enough, roughly 20 or more times the mass of our Sun, reaches the end of its life, it doesn't just fade out. It collapses in a fraction of a second and then explodes in a supernova so bright it can briefly outshine its entire galaxy. But the core that remains, if heavy enough, keeps collapsing, past neutron star density, past any known physics, into a singularity, a point of infinite density, surrounded by an event horizon, the boundary beyond which nothing returns. Inside a black hole, as best we can theorize, time and space swap roles. Moving forward in time becomes moving toward the singularity. You cannot stop falling any more than you can stop time from passing. The universe outside, from your perspective, would appear to fast forward. You might see the entire future history of the universe flicker past in the moments before the singularity. Or maybe not, because our physics breaks down at the singularity. General relativity and quantum mechanics, our best theories of reality, are incompatible with each other at extreme scales. Finding a theory of everything that unifies them is the holy grail of modern physics, the most astonishing accident in 13.8 billion years. Okay, universe, check. Physics, check. Matter, check. Now let's get to the really wild part, life. About 4.5 billion years ago, a cloud of gas and dust, the remnants of earlier stars, collapsed under gravity to form our solar system. Our sun ignited, the planets formed, and Earth, in a cosmic sweet spot, not too hot, not too cold, developed something extraordinary, liquid water. And in that water, about 3.8 billion years ago, something happened that remains one of the deepest mysteries in science. Chemistry became biology. Simple organic molecules, amino acids, nucleotides, formed and combined into self-replicating structures. The first life was single-celled, simple, invisible, but it could do something no rock, no star, no galaxy could do. It could copy itself, imperfectly, and those imperfections, mutations, became the engine of evolution. Over billions of years, natural selection shaped life from single cells into everything you've ever seen, touched, eaten, or loved. Every organism alive today, the bacteria in your gut, the oak tree in a park, the blue whale, the tardigrade on a parking lot leaf, all share a common ancestor. All life on Earth is family. About 300,000 years ago, one species, a Homo sapiens, developed something extraordinary even by life standards, consciousness, the ability to know that we exist. And here's where things get genuinely head-spinning. Consciousness is perhaps the biggest unsolved problem in all of science, and arguably in all of philosophy. We don't know what it is. We don't know how the electrochemical signals in neurons produce the felt experience of being you, of seeing red, of feeling love, of wondering whether any of this means anything. This is called the hard problem of consciousness, and it is hard in a way that physics problems are not hard. Physics problems we know how to solve even when we haven't solved them yet. The hard problem of consciousness, we don't even fully know what a solution would look like. Are you conscious because of the complexity of your brain? Would a sufficiently complex computer be conscious? Are simpler animals conscious? Is the universe itself, in some sense, conscious? These are not crazy questions. These are live debates among serious scientists and philosophers right now. And here's the thing that floors me every time I think about it. The universe is 13.8 billion years old. For the first 9 billion years of its existence, nothing knew it existed. There was no observation, no experience, no awareness. Just particles following laws, galaxies spinning in silence, stars burning in the dark with no one to see them. And then, on one tiny planet orbiting one ordinary star, in one unremarkable corner of one galaxy among 2 trillion, the universe woke up and began looking at itself. You are the universe experiencing itself. How does it all end? Okay, we've covered the beginning. We've covered the middle, which, for the record, is now. We are in the middle of cosmic history, which is a strange and beautiful place to be, but how does it end? The most widely accepted model is called the heat death of the universe. Here's how it goes. The universe is expanding, not just expanding, accelerating. Something called dark energy, which makes up about 68% of the universe's total energy content and which nobody fully understands, is pushing space itself apart at an increasing rate. Over trillions of years, galaxies will drift so far apart that, from any one galaxy, the rest of the universe will become invisible, moving away faster than light can cross the growing distance. Each galaxy will be alone in the dark. Eventually, over time scales so enormous they make the current age of the universe look like a blink, stars will burn out. Black holes will slowly evaporate through a quantum process called Hawking radiation, releasing their mass as a thin trickle of photons over 10 to the power of 100 years. That's a 1 followed by 100 zeros. When the last black hole evaporates, the universe will be an almost perfectly uniform sea of cold, diffuse photons and other low-energy particles. No structure, no gradients, no usable energy, no complexity. Maximum entropy, no life, no consciousness. No memory that any of this ever happened. That is the heat death, and it is, according to our best current physics, the likely fate of everything. You good, I know, that's a lot. But here's the flip side. We are here now, in the brief, improbable, extraordinary cosmic moment when the universe is alive with stars, with complexity, with life, with thought. The atoms in your body were forged in supernovae. The energy powering your brain comes from a nuclear reaction 150 million kilometers away. The oxygen you just breathed has cycled through billions of lungs over billions of years. You are impossibly old material arranged into a temporarily aware configuration existing in the most interesting era of cosmic history. That's not nothing, that's everything. What we still don't know. We've covered enormous ground, but honesty demands I tell you what we still don't know, and the list is humbling. We don't know what dark matter is. It makes up 27% of the universe by energy content. We can see its gravitational effects everywhere, but we have never directly detected a single dark matter particle. It passes through you right now, constantly, invisible and indifferent. We don't know why there is something rather than nothing. Why do the laws of physics have the specific values they have? Why is the universe fine-tuned, carbon, gravity, electromagnetism all calibrated to values that permit complexity and life? Is it design, multiverse luck, a deeper principle we haven't found? We don't know if we are alone. The universe has 2 trillion galaxies and perhaps 10 to the power of 24 planets. The chemistry of life uses elements that are everywhere, and yet, silence. The Fermi paradox, if life should be common, where is everybody? We don't know what time fundamentally is. We experience it. We measure it. But in the most fundamental equations of physics, time behaves strangely, and some physicists argue it may not be a fundamental property of the universe at all. And we don't know, perhaps most importantly, whether the universe is something that can be fully understood. Whether human minds, evolved for survival on a savanna, are remotely equipped to grasp the deepest nature of reality. Maybe. Maybe not. But the asking, the reaching, the pointing telescopes at the dark and wondering, that might be the most human thing we do. So, the ultimate guide to absolutely everything in the universe, we went from the Big Bang to black holes. From quarks to consciousness, from the first star to the last photon. From the mystery of the beginning to the mystery of what we are. And here's my honest conclusion after all of it. The universe is under no obligation to make sense to us. The fact that it mostly does, that mathematics describes physical reality, that we can understand the laws of stars and atoms and time, is one of the most profound and inexplicable miracles of existence. You are a pattern of information, briefly aware, floating on a rock through an incomprehensible void, somehow able to understand it, somehow able to be moved by it, somehow able to laugh at a YouTube video about it. That's extraordinary. If this video made you feel small, good. If it made you feel connected to something vast and ancient and alive, even better. If it made you want to go read about black holes or quantum mechanics or the origin of life, that's the whole point. The universe is the greatest story ever told. And we are, improbably, beautifully, briefly, characters in it. If you loved this video, smash that like button, subscribe, and tell me in the comments what part of the universe blows your mind the most. I read every single one. And I'll see you in the next video, where we tackle something slightly less ambitious. Maybe. Nobody has done it yet.